they say is the following. Suppose you have a typical generic point x naught, and you would like to know how to solve this problem in this neighborhood. And let's suppose that the flow lines, by the way, when you have this, x is the point in phase space, so this vector field is the phase space velocity. It's the velocity in phase space. So this thing, its field lines give you the flow lines, the phase trajectories. So suppose the field lines are like this. They need not be straight or anything like that. And this is some neighborhood u of x naught. Some neighborhood u of x naught. Then the statement is, except at critical points, at generic points, there exists a mapping from x to y such that this neighborhood in u is mapped onto another neighborhood v in the xi variable, in the y variable, such that the field lines, these field lines are mapped onto this. And that's the point y naught corresponding to x naught. So this is what the field lines look like. They look nice parallel lines. And what does that imply? It implies that the set of equations x1 dot is f1 of x, etc. This set of equations goes over into another set of equations in the y variables, which is y1 dot equal to 1, y2 dot equal to dot 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 equal to y dot equal to 0. So they say that it's guaranteed that there exists a mapping, a one-to-one mapping of this neighborhood into that neighborhood, such that the field lines are rectified. They're parallel lines. And that's a trivial set of equations to solve. Because now the solution just says y1 is t plus y1 of 0, and y2, y3, etc. are all the initial values. And then you invert the mapping and you get the solution. And because all this does is to straighten these lines, this is called the rectification for vector fields. That's their formal way of saying that you can always do this. However, this program is not going to help us integrate the system. By integrability, there are many definitions of it, and I'll give some precise ones. Roughly, for the moment, what it means is you should be able to take that set of equations, x dot is f of x, and write explicitly for me a formula for x dot of x of t. So I want to write x of t in closed form, or otherwise, I mean, I'm willing to be very broad-minded about what a closed form means, such a way that for arbitrarily large t, you should be able to plug in the value here and get what the correct value is. Let me give that as a zeroth order definition of integrability. That you can take this set of equations, differential equations, and integrate them to find a formula for x as a function of t. This is certainly not finding a formula. This is just numerically solving it, rectifying this vector field, but I want a formula for this. Explicit closed form, or explicit analytic form. That's a different question altogether. Now you might ask, why won't that happen? Why shouldn't that work? I mean, I do this rectification theorem and I'm back, I can do this. The difficulty is that when you're here, to go to a point here, you may have to have an overlapping patch and make a different map. And then of course in this patch, the vector field lines may look like this. And then you go to another patch, and the field lines may look like this here, and those field lines may look like this. So you need overlapping patches, like the process of analytic continuation for a complex function, for a function of a complex variable, which will take you all over phase space by a sequence of rectification theorems, applications of the theorem. The problem is that very often what happens is that this neighborhood in which this theorem works could peter out to a point. So you could start with a little neighborhood, and then it becomes this, then it becomes this, then it becomes this. So you peter out to a point because of the nature of this function f. There's another possibility which occurs even more often, and that is you make these changes of variables and you come back to where you started from and you're not back at the original chart.
So all
So
this
that
is in
is-
Y space.
Pardon me?
All this is in Y space.
All this is in,
Transform field.
or this space.
This space.
Or even this space, yeah. Or even this space. The neighborhood in which this rectification works could get could keep shrinking. So this thing here happens very often, and what it's a symptom of is that there is some kind of singularity, some kind of multiple connectedness somewhere inside. Or if you like, multiple valuedness of these functions f. If they're nice simple algebraic functions, you have one behavior. On the other hand, except for a linear function, nothing is analytic in the entire plane, in the entire whole of Euclidean space. They're always mapping singularities. So generically for nonlinear systems, the rectification theorem will not lead to a global solution. It leads to local solutions, but not global solutions. And as we know from many other cases, many interesting things happen when you have global properties as opposed to local properties. Locally you don't even see anything, but globally topology may change, all kinds of things could happen. After all, even the three-dimensional, just to give an analogy, even the ordinary three-dimensional rotation group looks very nice at on a local scale. There's nice Lie algebra, which is the algebra of SU2, but SU2 is simply connected, but SO3 is doubly connected. And you don't see that unless you go to the group rather than the algebra itself. So local things would be very nice, however, they may not give you global properties, and that's what happens in dynamical systems. So local rectification or solvability does not imply global integrability. This is the problem. Now the set of integrable systems is a set of measure zero in some sense, because they are exceptions rather than the rule. Now we're going to say a little bit more about integrability, especially in Hamiltonian systems. Integrability always means that you have some special circumstances. In general, you have some special symmetry in the problem. And that's what leads to integrability via constants of the motion. And we will talk about that. But right now, I just want to emphasize this again. I'll write it down, because it's very crucial. Solvability does not imply integrability. But integrability implies, of course, solvability. If you can write the solution down for arbitrarily large t, then of course you can write it down locally for small values of t. But the implication doesn't go the other way.
So here local and global, I mean,
Pardon me?
what is the difference between local and global in time?
In the whole of phase space.
In whole of phase space.
Yep. So there could be all kinds of complications in all of phase space. In some regions you may have periodic motion, in some regions you may not, etc. etc. These complications arise because of the singularities of this vector field F and more complicated
So
possible.
not possible the
Pardon me?
not possible getting the average quantity.
Yeah, if you have a simple chaotic system, for example, in three different variables, I said in two variables you don't get it in continuous time. In three, the equations could be very simple. There could be a nice quadratic nonlinearity, looks very nice, analytic and so on. But you cannot write down a closed form solution at long times. Worse, the error amplification will be so large that you cannot compute these solutions either
In time.
for chaotic systems. So that's the point. You may still in principle be able to do, given an initial condition, say what happens in the neighborhood of it, but if you have two initial conditions close to each other, it's entirely possible that the two trajectories will diverge exponentially and be extremely sensitive to initial conditions, and that's what happens. Then of course, once the divergence is exponential, then it's not even computable. And then the whole thing becomes nonsense, and that's where you need to resort to statistical methods. This is what I'm going to emphasize. Now, having said this, let's ask what this integrability actually implies. What does it really mean? And that has to do with the role of the constants of the motion. Now, all of you know that in this n-dimensional phase space, the phase trajectory is a one-dimensional object. However, when motion proceeds, certain combinations of the dynamical variables could remain constant. Now, the moment you have one such constant, say some function phi 1 of x equal to a constant, and somehow we discover under this evolution law that this combination, this function phi 1 of x is a constant. Its numerical value will depend on the initial conditions, but it's a constant of the motion. Now, what sort of object is this in n-dimensional space? It's a hypersurface of dimensionality n minus 1. So you have one constant of the motion, and just schematically, you have some big surface in this n-dimensional space on which this trajectory always lies. But that's not enough. The phase trajectory is a one-dimensional object. Suppose I discover a second one, phi 2 of x equal to C2 as well. Then what happens? This is an n minus 1 dimensional hypersurface. That's an n minus 1 dimensional hypersurface. Both these constants, both these quantities have to remain constant as the motion proceeds. Therefore, the phase trajectory must lie on the intersection of these two hypersurfaces. And what's the dimensionality of that? N minus 2. In this manner, it's clear that if the system is fully integrable, I must discover for you the large number of constants of the motion. How many? Independent ones, functionally independent ones. Well, if I have n of them, so this goes on all the way to phi n of x equal to Cn, then it's clear that the mutual intersection of all these would typically have dimensionality 0. Right? Because each time it increases by 1 and the dimensionality would be 0. So you won't have motion at all. Therefore, you cannot have more than n minus 1 functionally independent constants of motion. So the largest number you could have is up to here. That's immediately obvious. Now, of course, if you take two surfaces, even if they are very smooth, and you look at their intersection, this intersection could have all sorts of kinks and bends and things like that. So it could have points of cusps where in fact the derivative won't exist. But our starting assumption was that the derivative exists everywhere on the phase trajectory. So it means that these intersections have to be extremely special. And as you put more surfaces, they have to become even more special in order to finally produce an intersection which is a one-dimensional object and which is smooth and differentiable. That's why integrability is so rare. That's one way of understanding it. Because you need to have...
Please repeat the last point and once again.
Pardon me?
The last point, you are talking about the derivatives. Please repeat it once again.
Yeah, if you have a phase trajectory like this, at every point I've assumed that x dot exists. And therefore, the phase space velocity exists. There are no cusps and kinks and so on this phase trajectory. On the other hand, I take smooth surfaces and I start intersecting them. It's clear there could be corners, edges, and so on, unless they're very special smooth surfaces. So it's sort of a hand-waving argument already tells you that integrability must mean that these are very special constants of the motion. They're so nicely arranged among themselves that you end up with a mutual intersection which is very smooth. It won't happen in general unless there's some hidden properties here, like symmetries. That's the point I'm making. And that is also the reason why, if you just give me a random set of functions, f1, f2, f3, etc., it's very unlikely that the system is integral. It's even less likely that I might even find the constant of the motion. Yeah. You cannot find, most of the time you cannot find all the constants of the motion.
But it's there.
They obviously exist. They obviously exist. However, these constants of the motion, and I'll come to that, can be extremely complicated. As you'll see in a minute. You'll see, I'm going to give you a simple example where the constant of the motion is in fact very complicated to write down.
Can I find it out? Just squeeze it.
If we had a prescription for finding the constant of the motion, we could all go home. There isn't one. So we have to hunt using symmetries. So, but now let's come back to this, and I'll get back to this question of what constants of motion we could possibly have. In principle, you agree that if I find n minus 1 constants of the motion, then I found the phase trajectory. This never happens. Very, very rarely happens. But in principle, this is true. But now you could ask, what about the motion in extended phase space? And there you have n plus 1 dimensions, so extended phase space. X and t. So this is n plus 1 dimension. In this extended phase space, also you have a trajectory, but it's completely clear that you need one more constant of the motion now, because you're now in n plus 1 dimensional phase space, so you need n constants of the motion. But all n of them cannot be time independent, because then there will be no motion. So this immediately tells you on elementary grounds that there must be at least one constant of the motion which is explicitly time dependent. So that's a little bit of a strange notion for students to digest when they first see this, but it's implicit. It's very clear that a constant of the motion will be explicitly time dependent. There could be explicit time dependence in a constant of the motion. After all, let me go back and explain where this comes from. It's worth remembering.
Then why it's called constant of motion?
Because it remains constant in time. It remains constant in time. Because it's a function of the x as well as the t, and the dependence of x on t will compensate for the direct t dependence explicitly. That's the whole point. Well, you're already familiar with this, except that perhaps you didn't appreciate it in that language. You know, when you write down a constant of the motion in quantum mechanics, which is a language people are more familiar with than even classical mechanics, if you have a constant of the motion f, then you say that df over dt, ih cross df over dt, is the commutator of something in something. Yes, plus this. There's this fellow sitting there, right? Plus ih cross times this. There's that fellow sitting there. So a constant of the motion is something where df over dt is 0. If therefore f has explicit time dependence, this quantity is not 0 and it must cancel this. So that's the real definition of a constant of the motion. What does this do classically? What does this do classically? It of course becomes df over dt equal to f. We'll talk a lot about Poisson brackets as we go along. It sort of exemplifies the symplectic structure of Hamiltonian mechanics, so we'll talk about that in some detail. So you agree that you need to cancel this term with this term here, and then you have a constant of the motion explicit. Let me give you a simple example, very simple example. It is so simple that it's laughably simple. Let's look at a one-dimensional motion, a point moving on a line, a mass moving on a line. So the phase space is just x and p, and my Hamiltonian is p square over 2. Free particle moving in one dimension on the x-axis. What are the phase trajectories? There's one constant of the motion, and that's the momentum. So it's clear that p equals the constant of the motion. There's no dependence of p on time at all. Okay. So what does that imply? You give me an initial p0. I start with this point with the p0, and of course the system keeps moving to the right. If I start with the p0 on this side, the system keeps moving to the right. These are the phase trajectories. If you start with p equal to 0, then the system remains where it is, it doesn't move at all. The whole of this line is a set of degenerate critical points. That's a constant of the motion. However, and that's all that's possible in the plane. Because if you have a second constant of the motion which is independent of p, because you should say, well, you could say p squared over 2m is also a constant of the motion, but that's not functionally independent of this. Once you give me this, that's gone. But if you had a second independent one, it would typically generically intersect the first one here, and then of course the motion would have to be restricted to that point. So that can't happen. On the other hand, in phase space, in the extended phase space, so let's bring the t out in this direction. In this space, you need a second constant of the motion because p equal to constant is now a plane. You need one more constant of the motion, and that has to be t dependent. And what's that equal to?
In terms of Q, so just write it.
So let's write down Hamilton's equations of motion and solve them, right? So x dot equal to delta h over delta p equal to p over m, and p dot equal to minus delta h over delta x equal to 0. This implies p equal to p naught for whatever given value, and of course this guy here will imply x equal to p naught p over m plus x naught. That's the solution. But now this implies immediately that x minus pt over m is a constant of the motion whose value happens to be equal to x naught. Just as the numerical value of this constant of the motion happens to be the initial condition. Similarly, in the other case, the value of this constant of the motion happens when now you see where this comes from. You see that if you plug this in, if you do this, you indeed discover that the t dependence here is cancelled by the x dependence in a trivial fashion. So that's a constant of the motion. And this is not a planar surface or anything in the three-dimensional space. This is a fairly complicated surface. Some kind of hyperboloid or something. But when it intersects that other constant of the motion, when it intersects, it just says x increases linearly with t on any plane p equal to p naught. And the slope of this intersection keeps changing, which is why it's proportional to p naught. So already you see this, it's not such a trivial matter. There's an extra constant of motion. Now often in textbooks you see the statement made that the initial conditions are the constants of the motion. I can't think of a statement more calculated to confuse students of physics than that. What's meant is that the numerical values of the constants of the motion are determined by the initial values. It's not the same as saying that the initial conditions are constants of the motion. Constants of the motion are functions of the dynamical variables and possibly time. So you agree that there's one more constant, that's it. In this problem, this is all it is. Well, now go to Hamiltonian systems. You know what the integrability criterion is for a Hamiltonian system. So let's look at one which is got a lot of q's, 2n, and then a lot of p's up to pn. In this case, n is 2n, the number of dynamical variables. I write these equations of motion down, etc. And then if this Hamiltonian is integrable, if it's integrable, I need some conditions for it, and they are the so-called Liouville-Arnold integrability conditions, which I'll talk about later. You already know what the constants of the motion are. What do you do to integrate a Hamiltonian system of this kind, if it's integrable? You make a canonical transformation. You make a canonical transformation, which means that you make a transformation which preserves the Hamiltonian structure of the equations and the Poisson brackets to a new set of variables in which the Hamiltonian does not depend on all 2n variables but only n of them, the so-called action angle variables. And the Hamiltonian will be a function only of the action variables but not the angle variables. And then the system is integrable completely. The n, little n action variables are constants of the motion. The remaining constants of the motion are determined by the initial values of the angle variables, but they're explicitly time dependent. So you have a problem there where if it's integrable, implies that n t independent constants of the motion and n t dependent constants These are your so-called action variables, and these are the initial values of the angle variables. They have a dependence exactly like this x minus pt over m.
So is it like this state dependent system? I mean, can it be possible like without doing the canonical transformation? I mean, in the actual XMP.
Yeah, sure. Sure, except that, yeah, the statement is that for a Hamiltonian system with that structure to be integrable, a necessary and sufficient condition is that the Liouville-Arnold criterion be satisfied, n of these constants of motion in involution and so on. But then it implies that there exists a smooth change to action angle variable such that this is true. Now finding that is very difficult. That's why you give me an arbitrary Hamiltonian and I have no way of finding out if it's integrable or not. There's no algorithmic procedure for this. On the other hand, I use experience. I know there are a few cases like the harmonic oscillator, the Kepler problem, and so on and so forth, which are integrable. And that's also the reason why if someone discovers a new integrable Hamiltonian system, which is not trivial in many variables, everybody celebrates, because then the whole industry springs up trying to write everything they can about it, like the closure of Sutherland models, etc., etc. Whenever you have a new integrable system, especially if it's a nonlinear one. But it means there's a hidden symmetry. The problem. Yeah. Yeah, it's not. I've not yet defined it. I only said global integrability. You can write down the solutions and things like that, but I haven't defined integrability yet. There are many classes of integrability. Is it analytic? Is it algebraic? Is it the Hamiltonian sense, etc., etc. I took a rough operational definition. You can write down closed form solutions, or you can write down long-term, arbitrarily long-term solutions. So much for constants of motion. We'll return to that over and over again. By the way, one quick question in anticipation of what we will do later. These constants of the motion, either classically or quantum mechanically, play a very crucial role, not just in the integrability of the system, but in generating the symmetries of the system. So they have the physical meaning, and we will see this explicitly, that they act as the infinitesimal generators of the symmetry groups of the system, these constants of motion. And you already know this because if you give me, let's take an example. Let's take the example of n particles, classical particles, interacting with each other by pairwise potentials, and ask what are the possible constants of the motion that we can read off. So my Hamiltonian is a function of all these variables, momentum, position, etc. So I equal to 1 to some n particles, pi squared over 2 mi, doesn't matter, plus a potential, which I will assume is conservative. The forces are conservative, they are derived from a potential. And let me go one step further and say there are pairwise interactions between the particles, which are directed along the line joining the two particles. So this would be something of the form Ij, and no self-interaction, some potential, which is a function only of the pairwise differences. And now I ask, what are the possible constants of the motion here? First of all, n in this case is equal to 6n, because there are 3 degrees of freedom for each particle in 3-dimensional space, 3 coordinates, and therefore 3n generalized coordinates, and therefore 6n phase space variables. It's a large system. And already you can see things can become very complicated, because if n is 1, there's no problem. If it's 2, there's already a problem. If it's 3, 4, and so on, you run into serious difficulties. Okay. Now, what are the constants of the motion that you can read off from here? Obvious constants of the motion.
Momentum.
Well, it's clear that the total momentum is going to be a constant because there's no external force from the system, and we can prove this very rigorously. So, capital P. First of all, the Hamiltonian itself is a constant of the motion. If it's an autonomous system, in other words, the Hamiltonian is explicitly time independent, then it is a constant of the motion, automatically. This quantity here, I equal to 1 to n, pi is a constant. These are 3 more constants of the motion. There's no torque on this system, right? Therefore, the total angular momentum about the origin must be a constant of the motion.